All right, so let's get going on today's class. So today, first off, welcome back. I hope everybody had a great spring break. And what we're going to do today is we are going to finish up our look at Chapter 7, the long-term memory encoding and retrieval. And then we're going to begin our look at Chapter 9, which is all about knowledge, kind of builds on what we learned about memory, but then goes a little bit deeper to figure out how exactly do we store and work with the information that we know are knowledge. So what we're going to do is we're going to take a look at a brief recap of infantile amnesia and what encoding specificity had to say about that. We're going to see a very kind of special case of encoding specificity that happens to children when they're very, very young, which is the development of a sense of self and that impact on memory as well. And then we're going to take a look at the idea of memory reconstruction and its implications for dealing with traumatic memory experiences. So we're going to see how this basic idea that we actually reconstruct our memories when we remember them. We actually take pieces of memories from all over our long-term memory store, put them back together, and that makes them vulnerable, how that's being used to treat patients who have had traumatic experiences, that the memory of which is impacting their mental health. All right, so we'll have an encoding specificity recap. We'll take a look once again at infantile amnesia, and then what the self kind of brings to that paradigm. And then we'll take a look at memory reconstruction and talk a little bit about science fiction, and then take a look at science fact. All right, so if you recall, hopefully now that you're back in the room, you got all the cues around. Encoding specificity is the idea that when you encode a memory, you also encode the context around that memory. So you're trying to remember one specific thing, such as what encoding specificity is. But when you're making that memory, you're also encoding everything that's around at the time. So you're encoding me, you're encoding the screen, you're encoding this classroom. And those can be used as context, as cues, to help you retrieve that memory later on. So we took a look at how this could possibly account for infantile amnesia, which is the phenomenon where prior to a certain age, you don't have memories. So if you think about the earliest memory that you have, it'll probably be from when you were around 3 years old. So what happened to all those, what happened to that 3 years of your life? It actually, during spring break, we actually came across, I think it's like the 4-month anniversary of when I fell off my bike and I got a concussion. And I am missing approximately an hour of my life. I do not know how from when the time that I fell over to the time when I was standing in front of my class going, I can't remember what we did last week right now. That memory is gone. And it's bizarre, right? It's when you lose a chunk of your life, it's weird not to have that continuity. And yet we all live with that. We got 3 years of it where we have no idea what happened to us during that time. And we brought in the idea of encoding specificity to account for this with the idea that your context as a baby is radically different than your context is right now. So for all those memories of you as a child, you lack the context that can be used as cues to help you retrieve that memory. So this is your visual world right now, but as we saw last time, the visual world that you had as an infant was much, much different. Infants, when they're born, their vision is about 2400. So if you got 20/20 vision, that means that you can see at 20 feet what an average person can see at 20 feet. Babies can see at 20 feet what an average person can see at 400 feet. So their vision is horrible. So this is the context that they encoded with their memories. When that context is gone, maybe that's why they cannot recall those previous memories. And when you take a look at the world of an infant compared to the world of an adult, it is a vastly different experience. So just the size of things, just the scales of things, and as we ended with, just the experiences that you have, right? I cannot remember the last time I was picked up and thrown over the shoulder and carried, right? But if it ever happened again to me, maybe memories of a trip to the beach will just come flooding back because the context will be reproduced. So that leads us into our look at infantile amnesia and the self. And we're going to see a really interesting study that was done that took a look at whether children had developed a sense of themselves, a sense that they are an entity that is separate from other things, and what impact that had on their memory.
This is a profound moment in what...
All right, so that was a study there again that showed that one of the key things that occurs, one of the key determinants of whether or not you're going to recall autobiographical memories is this development of a sense of self. So thinking about encoding specificity, what is it about the sense of self that might be incredibly important in order to retrieve these memories?
Meaning?
Meaning, so...
That, like, because I think when it's autobiographical, kind of like how you remember things better when they're more than just, like, the different levels of processing, because it means something, so you can relate it more. So if they know who you are, then it's not just, like, surface level stuff, because it impacts you more. Okay, so the sense of self might give you a deeper meaning. It might allow you to interpret things in a more meaningful, deep way. So that's one possibility for why that sense of self will then allow you to recall things later on. Is there a more kind of specific way, though, to tie it into encoding specificity? So I'll give you a hint. When you're in this room, there's a certain context that you have in here in order to encode these memories. And as soon as you leave this room, that context is gone. So you will then have, hopefully, only a slightly more difficult time to remember the information that you learned in this particular room. When you go to any other location on campus, there's going to be that context there. And when you encode that information, again, you'll be more able to recall it within that context. And when you go to your study room, that is, again, a context that you're going to help encode your information. So you have these contexts that change in every single environment that you're in. But what would be one context, I'll put it in quotes because it's not an environmental context, but what's one context that hopefully will always be with you, regardless of where you are?
Your like sense that you like exist in the world and like there's things around you, I guess.
Exactly. So basically, your sense of self is in some ways the ultimate context, because it does not matter where you are. Your sense of I'm here, I'm somebody, I'm me is always going to be there. So that idea that the sense of self might act as just that perfect cue, that ultimate sort of context, really sort of sheds light on this in terms of the encoding specificity hypothesis, because if you do not have that sense of self, like the younger children didn't, then there's no context to help you retrieve it. But when you do have that sense of self, and you're in that situation again, and they're like, oh, where's the line? Where was he 2 weeks ago? You can think to yourself, all right, I was here, I'm somebody, I pinned this memory to that context, to that idea that I'm somebody. Oh, of course, the lion's in the bottom drawer, that's where he sleeps. So it could be that because the self is such an important contextual piece of memory information, that we've lost all those memories prior to our developing of the sense of self, just because we don't have that shared context. So there is not a memory, I would argue there's not a memory that you have that you would not be able to tie to your sense of being aware of who you are, right? And it could just be that because of that very powerful context, anything that happened before that development of that sense of self is just gone because that cue is not there. All right, any other questions? Oh my gosh. All right. Well, we got an IU emergency alert. So we are going to go to the nearest NWS shelter. So if everybody can get up out of their seats. And we are, so let everybody get back in.
Oh, sorry.
All right, so let's get back going. So we kind of finished with our look at infantile amnesia and the self, the idea that the self kind of provides the ultimate context. And if on the exam you're having trouble remembering any of this stuff, try to remember the tornado warning. Maybe that'll jog your memory because you've all encoded that context along with this information. All right, so we're going to wrap up our look at memory by taking a look at a really interesting study that uses reconstructive memory to deal with, to help people who are dealing with traumatic memories. So memory reconstruction is, it's a novel idea. It kind of turned memory research on its head in the 90s when it was kind of discovered that memory is not locked away. Your memories are not locked away in a filing cabinet in your mind that you can just go and access. Your memory is actually kind of scattered around in pieces. And when you try to remember something, you grab all those pieces and you put it back together. You reconstruct it. So whenever you recall something, your memory is literally being remade, reconstructed. And it's not just that they're being accessed like files. So what this means is that your memory is being rewritten every single time that you recall your memories. And this procedure of rewriting it, as we're going to see, makes it vulnerable to interference, makes it vulnerable to interrupt procedures that re-encode that memory. Because just the way that you grab it out of storage, put it all back together, you then, when you are done with it, have to take it all apart and re-encode it and put it back together as well. So this idea has been used in science fiction where so it's been used in science fiction like the eternal sunshine of the spotless mind, where because of this memory reconstruction, your memories can actually be erased. So you can actually, much like in the movie, do a procedure where you can erase your movie. So for those of you that haven't seen Eternal Sunshine of the Spotless Mind, highly recommend it. But here's a brief trailer. Spotless Mind. And that was a straight up science fiction movie. But it did have that premise, that idea of focused erasure of a memory. And whether or not the sort of dilemma of the movie is whether or not you would want to remove those memories. But we're going to actually take a look at research now that shows that you actually can do almost exactly what they were talking about in this movie, which is the focused removal of certain types of memory. And it has to do with the idea of memory reconstruction. So you're going to see in this experiment what the researchers are doing is they're having a particular individual recall a traumatic memory, and then they're doing a treatment, a pharmacological treatment that impairs or inhibits the ability to then restore that memory. So they're recalling the memory to make it vulnerable, and then they're using pharmacological intervention to prevent it from being fully restored. So we're going to see the story of Genevieve, and once again, see how this basic idea of memory reconstruction is being used to help this particular individual. As you can see, I mean, a lot of stuff was going on in that one particular video. But very interestingly, it tells us a couple of things about memory. Number one
memory is being reconstructed. So that that idea that psychologists had for decades, the idea that you have a memory, it's stored in your brain, there it is, it's like a filing cabinet that you can go to and find your memory. If you forget something, it was because the memory was destroyed or it was misfiled somewhere, but it was there and it was intact. The new research kind of showed that no, what you're doing is you're pulling together pieces of these memories and then reforming them. And when you reform them, you then again have to kind of re-encode them. And this is being used to break up the memories for Genevieve in this traumatic instance. Interestingly, it's working only on the emotional aspect of her memory, not on the actual autobiographical memory. So she will never forget that she was raped. That's part of her timeline. That's part of her autobiography. But importantly, the emotional aspect of that memory is no longer going to be extreme enough in order to cause her harm. So if you notice the timeline on this, this treatment began 9 years after her assault. And in those 9 years, her trying to deal with this memory on its own and its implications led her to have those post-traumatic stress disorder symptoms, led her to be afraid of going outside, led her to be afraid of people. And this is when things get beyond the threshold of just being an intense memory versus being, a mental health issue. So when it affects your ability to do your work, when it affects your ability to do relationships with others, when it's impacting your life that massively, that's when it crosses that line. So she had crossed that line and for 9 years was trying to deal with this. And it's very interesting that in 6 weeks, her emotional levels of her memories are down 30% and now is below the threshold of what is considered to be, post-traumatic stress disorder levels. So just in 6 weeks, because of the research that psychologists have done, she's basically on her path to getting her life back. And the last thing I want to mention about this is that this research, this idea of reconstructive memory, which led to the idea that you can use this beta blocker to impact the memories and this whole treatment paradigm, this all came from a very famous study that gave subjects lists of words to remember and then had them recall those particular words. So they would give them a list of words that were all associated with a non-presented word. So they would have things like snore, bed, nighttime, drowsy, dreaming. And you would have to recall that list. And nowhere on that list was the word sleep. And yet people would falsely recall sleep. And that was a huge finding because previous to that finding, people knew that you could forget things. But they never knew that you could remember something that didn't actually happen. People were remembering, oh, I saw sleep. And you're like, well, that's impossible. It couldn't have happened. You didn't see that on the list. So that kind of turned memory on its head and said, you know what, we're not actually accessing files in order to remember things. We're constructing our memories. And when the construction leads to the fact that sleep was there, we're like, yeah, sleep was there. So this whole helping of this individual here came from a study that asked people to recall lists of words. So that is just something that oftentimes I find people forget in psychology. When you're in the lab and you're like looking at reaction times and you're looking at how many words did you recall, it's very easy to kind of dismiss it and say, oh, that's, big deal. So your reaction time is 10 milliseconds slower. So you saw sleep when sleep wasn't there. No big deal. And it's important as psychologists to remember, no, huge deal, massive deal, right? You just got to see it for what it is and take it out and put those implications and work on it and, to help the lives of others. Any comments on this before we wrap up our look at memory? Questions? All right. So that was it for memory. So what we're going to do right now is we're going to start our look at knowledge. We're going to start our look at chapter 9. We'll see how far we get today. I don't want to rush through any of this because the idea of knowledge, how we represent knowledge, that is a very, very important topic in cognitive psychology as well. So what we're going to do today is we're going to introduce the idea of a semantic network. And this is the basic idea of how our knowledge is stored in our minds. And we'll see if we can get to Colin and Quillian's hierarchical model. This was a very influential model of how our knowledge is stored. Maybe we'll get to the spreading activation model when Collins went off with Loftus and came up with that model. We'll do the COG lab, and then we'll see about implications, once again, that these models have for how our minds work and what that means for our lives and our society. All right, so a semantic network. So semantic knowledge, knowledge of facts, knowledge of things, right? So if you remember in long-term memory, we had episodic memory. This is the memory of things that happen to you. We had semantic memory. This is the memory of knowledge that you know. And we're going to specifically now take a look at how is the knowledge that you know, the things that you know, the facts that you know, the theories that you know, the things that you're learning in this class, how are they represented in your mind? So once again, this is in the mind, not in the brain, although you're going to see clear parallels with how this might actually be implemented. So in the mind, your semantic knowledge can actually be thought of as a list of facts, a list of propositions, a list of statements of the things that you know. So it's almost as if somebody ever came up to you and said, here's a pad of paper, write down everything that you know. And you just wrote down a whole bunch of statements of everything that you know. That's what we consider to be represented in your semantic knowledge. So you can think of it as a list of propositions. And one of those propositions might be a statement like this: Lincoln, who was president of the United States, freed the slaves. Right? So you might have that listed in your mind as part of your semantic knowledge. So the question is, how is this proposition represented in your mind? So this, the fact that you might know this, that is that conceptual level. Yes, this is something that people would say, I know that fact or that piece of information, but how is it represented? And the idea is that these propositions, they're represented as nodes, as kind of endpoints that can either be relations or they can be arguments, they can be things, or they can be relationships between things. And then also you have links between the nodes. And this is that idea of a network, right? These nodes and these links are going to form a network, and that is what is actually in your mind when you represent this information. So let's take a look at what a semantic network might look like. So here's your mind, and here is one of the nodes. So we have a node. We'll represent some of these by circles. Other ones, arguments will and links will represent by lines. So we got a node, and that node is the agent node. And that agent node is the idea of Lincoln. So we have the idea of Lincoln, and Lincoln is going to be the agent, the thing that is doing something in this semantic network. So that is related to another node. Sorry, that is related to another node. So we have the relation, we have the argument. So Lincoln, the agent, is related to the idea of president of. So right now, at this point, we have Lincoln is what? The president of. And that's all that you would know if this is what you had represented in your mind. We can add another link to another node, and that is now to the relation of an object, and that object is now the United States. So now we have Lincoln is the agent. What is he? He's the president of. What is he the president of? The United States. So this semantic network here, these connections here, represent Lincoln, president of United States. We can then add to our semantic network. So we can have another separate idea, where we have agent once again linked to Lincoln. And now the relation is not president of, but freed. And the object in this case would be slaves. And now we have the complete semantic network. So now we have Lincoln, who was president of United States, did what? Freed the slaves. And notice that you can't get confused in this particular semantic network here. So you wouldn't go United States freed president of Lincoln, who was slaves, because the relations there are tied in with the nodes. So that's one way of, or one idea of the semantic network. How we represent knowledge in our mind would be in a network of relations that is like this. All right, so let's say that that was represented in your mind. And let's say that you were walking around one day, and let's say there was a tornado warning, and we did not get to shelter. And you are, the tornado comes, and you're running towards shelter, and unfortunately a brick hits you in the head, and you get a little bit of brain trauma. And that brain trauma affects this node right here. And instead of Lincoln, it changes to Bill Gates, right? So this is a very cartoony example. It's not going to actually happen. But let's say that that's what happens. You get hit with a brick, and Lincoln changes to Bill Gates. Now, what you have represented here is not Lincoln, who was president of the United States, freed the slaves. Now you are under the impression that Bill Gates, who was president of the United States, freed the slaves. So let's say that you continue to try to get to the shelter. You get hit in the head once more with another brick. And instead of United States, that now gets changed to Microsoft. So once again, you get hit, the node changes, and this semantic network is now representing Bill Gates, who was president of Microsoft, freed the slaves. And once again, another brick to the head. And all of a sudden, freed gets changed to program. Now your semantic network says Bill Gates, who was president of Microsoft, programmed the slaves. And you get one last brick to the head. Slaves changes to Windows. And now you have miraculously come back to a true statement, which is Bill Gates, who was president of Microsoft, programmed Windows. So you can see how anything that you want to represent, any piece of knowledge that you might have, can be represented with these semantic networks. And if you put those two side by side, you can see how the structure of the network is basically the same. It's the same kind of pattern, but the arguments of the network change the meaning. So Lincoln, who was president of the United States, freed the slaves. Bill Gates, who was president of Microsoft, programmed Windows. Completely different statements, both represented in a semantic network. All right, any questions so far? All right. So the question then is, how is this semantic network organized? So we have the possibility of a semantic network, and then researchers wanted to know, well, we have this possibility of organizing our knowledge, but how is it actually organized? What kind of structure? Is it hierarchical? Is it just, put together haphazardly? Is there any order to how our semantic networks are organized? And one of the first ideas was Collins and Quillian's hierarchical model. And this was the idea that we actually do have a hierarchy of ideas, and that categories are organized under supercategories, and categories lead into subcategories. So let's take a look at an example of this. So let's say that you had the concept of animal. So in your semantic network, you have a node, and that node is the idea of animal. That node can have features that are attached to it. So you would attach features that animals have. Animals have skin. Animals can move around. Animals eat. So you would have all these features that indicate what animals do. And then below that node, and animals breathe. And then below that node, you would have any other concept that is related to being an animal as being part or in the category of animals. So birds are animals. So they would form a subcategory of animals. And birds would also have connected to them features that only birds have. So not animals, but birds have these. So birds have wings. Birds can fly. Birds have feathers. And then below that, you would have subcategories for particular types of birds. So canaries, you know, they can sing. Canaries are yellow. Ostriches, they are tall. They can't fly. They have long, thin legs. So this is the idea that you organize your knowledge in terms of this hierarchical categorization of ideas and then an attachment of features to the relevant category. So you don't have to attach has feathers to canaries because canaries are related to birds or connected to birds, and we know that birds have feathers. You don't have to attach eats to ostrich because ostrich is attached to bird, which is attached to animal, which has the feature of eats. And then on the other side, you could also know about fish. And for fish, you would have that they have fins, they can swim, they have gills. And then you would have different types of fish like shark and salmon. Shark can bite and they are dangerous. Salmon is pink and it is edible. So this was the idea of how our knowledge is organized. It's organized in this very clean hierarchical model. And we're going to see that it seems like much of our knowledge might be organized in this way. But spoiler alert, almost nothing in your mind is clean and highly organized. So that's where future models come in. But let's take a look at this one first and some of the implications that it would have. All right, so this was again a model of semantic knowledge, conceptual knowledge. It is a propositional network, much like the semantic network. And it came with its own assumptions of how this model works, how this hierarchy would actually work. So assumption number one. Assumption number one was that retrieving any property is going to take time. So if you need to retrieve something from this hierarchy here, right? So if you need to retrieve the idea of has wings, that's going to take you time to do. It takes a certain amount of time for you to access that hierarchy and say, yes, has wings is part of my hierarchy. So retrieving any of these properties takes time. And also traversing the hierarchy takes time. So if you're thinking about canaries, it takes time to then think about birds and then think about animals, right? If you're thinking about birds, it takes time to go up and think about animals. So moving along these links here, that's going to take a little bit of time. It's not an instantaneous move from one level to the other. All right, assumption number two, the times are additive when one step is dependent upon the completion of another. So the time that it takes you to answer questions about your knowledge is going to depend upon where do you have to go in that model, and that's going to be an additive time. So if somebody asks you, is a canary yellow? It's going to take you a little bit of time to say, oh, canary is yellow. Yep, that's part of my semantic network. Yes, a canary is yellow. If somebody asks you, does a canary have feathers? It's going to take you more time, according to this model, because you now have to start a canary, and instead of just immediately accessing has feathers, notice has feathers is not there. So you now need to jump up to bird, and now you can access has feathers. So you got two moves now. You got to go up a hierarchy and access a feature. That's going to take you more time. And if somebody says, does a canary eat? You would have to say, all right, here's canary. I got to go up to bird. I then got to go up to animal, and I then got to access eat. And the idea is that each of those moves takes time and adds to the previous moves. You have to go up the hierarchy one ladder at a time, one level at a time. You can't just jump from canary all the way up to animal. All right, assumption number three. The time to retrieve a property is independent of the hierarchy level. And what that means is that if I asked you whether an animal eats, accessing eats for this super category of animal, this high level category of animal, accessing whether an animal eats will take exactly the same time as accessing whether a canary is yellow. And that'll take exactly the same time as accessing whether a fish has gills. So it doesn't matter if you're in the top, middle, or bottom level of the hierarchy, accessing a feature or accessing a property is going to take exactly the same amount of time. All right, so the question that they asked, and we'll just introduce this question, is what would happen if conceptual knowledge was actually organized in this way? And what they tested, and we'll see the evidence for this next time, is that if your knowledge is actually organized this way, if they got it right, and Collins and Quillian actually figured out how the knowledge is stored in your semantic networks, then you're going to have very different reaction times to verify different sentences. And the key is going to be how many levels do you have to traverse in order to answer that question. So the idea is that, and this is what we'll end for today, the idea is that if I ask you, is a canary yellow? That should be very quick because you only have to access a property. You only have to access a feature to answer, yes, a canary is yellow. But if I ask you, can a canary fly? You then have to go from canary up to bird. That takes time. You then have to access can fly. So it's going to take you longer to answer, can a canary fly? And then finally, if I ask you, does a canary have skin? You're then going to have to say, all right, here's canary. I'm going to take some time, go up to bird. I'm going to take some time, go up to animal. Yes, it does have skin. So that's going to take you even longer. So what they did was they basically gave subjects sentences, and depending upon how many hierarchies had to be traversed, they took a look at whether reaction times actually indicated this structure. So what they did was they gave them sentences, and they said, as quick as you can, tell me if this is true or false. And they would say something like, sharks have skin. And people would be like, true. And be like, okay, how about salmons are edible? True. And they wanted to see if you didn't need to traverse any hierarchies, would you be faster than statements where you have to traverse one hierarchy? And then would those be faster than statements where you have to traverse two hierarchies? And we will take a look at that data, what they found, next time to see if our knowledge is actually nicely represented by this hierarchical model. All right, so that is it for today. If you came in late, make sure that you sign into the sign-in sheet, wherever it might be. And I will see you all next time.